Thanks.
Good luck, Sergio.
Thanks, Vlad.
Big fan of the work.
Okay. So I have here. Okay, so you already know me. My name is Sergio, and today I'm going to talk about Rootstock work on creating a new bridge that is called the Union Bridge. And it's moving? No, this one, maybe. This one. Hey. So why a new bridge? That's what I ask myself sometimes. Well, I started working on bridges in 2012. I actually designed the first validating bridge that ever existed. It was called P2P TradeX and was meant to connect Bitcoin to some other blockchain that didn't exist. And I introduced the idea that one blockchain could validate the block headers of another blockchain. And then marvelous things could happen from that. Obviously, afterwards, I designed the Rootstock sidechain, which was the first production-ready sidechain for Bitcoin. I designed the Rootstock merge mining system and also the bridge. I contributed to the drive chain by designing and publishing the first Bitcoin improvement proposal. I was the opcode called count acknowledged. I discovered a key vulnerability in Bitcoin Merkle tree, which affects all bridges that exist today. Like every single bridge that is a validating bridge must protect against this vulnerability because of a problem with Bitcoin Merkle tree. I designed 2 other bridges, so my life in the last 10 years has been around bridging. But currently, I work at Roostock Labs and trying to help improve always from the scientific side the Rootstock blockchain. So first, few words about Rootstock. You probably know it. Rootstock is a Bitcoin sidechain. It's merged mined with Bitcoin. It has more than 50% of Bitcoin hash rate. It's super aligned with Bitcoin in the sense that the native currency of Rootstock is Bitcoin and not else. You pay fees with Bitcoin, etc. And also we pay Bitcoin miners for the merge mining work. And so I think it's one of the most aligned layers 2, apart from obviously Lightning, layers 2 that is fully aligned with Bitcoin. So what's the motivation behind Union? Why still another bridge? So the motivation is that the Rootstock bridge currently is kind of a federated bridge. The keys are protected with HSMs, hardware security models, and you need to compromise 5 of 9 hardware security models to extract the private keys, which is terribly hard. And inside each one of these hardware security models, a light client is run. So basically, you cannot extract the public key, the private key. You cannot back up the public key. You have to give an enormous amount of hash rate to the hardware security models because they follow the best chain. So essentially, it's very hard to break. We also have public attestations that anyone can detect and verify which is the firmware that is being run. But there is a problem there. It's not permissionless. Like if I want to participate in being one of the validators of this bridge, I can't. Because there is this problem that I'm talking more about later. It's called the security dilution, right? If you let anyone come, then obviously you lose the security. And the other problem is that we are somehow depending on Ledger, the company which manufactures the HSMs, that they don't put any backdoor on the devices, which I think they don't, but at the end of the day, most Bitcoiners will not be 100% comfortable. So the federated model, also known as T out of N security model, is that you need to compromise T parties, or in other words, you need T parties to be honest for the system to be secure over a committee of N parties. And as I mentioned before, this does not allow you to be permissionless, because if more parties come, even if they stake, they can civilly attack the system, dilute the security, and take control of the funds. So that's why we cannot do that. But then we have these fantastic ideas of validating bridges I talked to you before, which have a completely different security model. So let's think a little bit more about how this security model works. So the first insight you learn just when you start working on validating breaches is that a validating breach needs to be an interactive system. It cannot be a system where there's just one party that sends the headers of a foreign chain and feeds this. Because if that is the case, then this party can collude with the block producers of the foreign chain to basically produce any fork they want, feed it to the closed system, and then take all the fun. So you need to be a competition, like anyone should be able to send these headers to this system. The second insight you learn very quickly is that if you try to do that, obviously with blockchains that have a very high block rate, is that it's terribly inefficient and very costly. So what everyone does is, instead of sending one header at a time, they are sending a proof, a succinct proof that say, okay, this 100 headers, this 1,000 headers, is the fork I want to prove that have this withdrawal event that I want to show to this system, right? But again, if you want to preserve this interactivity property, you need to offer a counterproof. So someone else must be able to come exactly 1 moment later and say, okay, no, this is the canonical chain. This is the longer chain, which is the valid chain. Okay? So that's why I said that any validating breach needs to have this property I call one of infinity. Like there is an infinite amount of community members. You just need one, to be honest, and to have enough funds to send this counterproof. Okay, so we have this T of N security model, that is the federated model. We have the validating breach model, one out of infinity, and there was nothing in between. Until October 2013, Robin Linus created this new model that is one of N, which is kind of in the middle. You still have a committee of N members, but you only need one to be honest. Okay, so this allows you to create a new kind of breaches. We call them BitVM breaches. There are many flavors of this. So now we really can have a permissionless system, because let's say we start with 3 members. I'm part of the committee because I want to put my savings in Rootstock, so I want to be part of this committee that is controlling the breach. And so I'm the green dot there. I don't know the other parties. They are anonymous. But if this grows and grows, I don't care. Like, I'm sure that if I'm there, I'm going to protect it, okay? And I'm going to challenge anyone trying to steal the funds. So now we get to know what is this union breach. So I'm going to read it. The union breach is an innovative, trust-minimized, and permissionless, this is the properties I told you about, two-way peg system based on BitVMX, and I'm going to explain what this is. And it's a technology designed by Roostock Labs for Rootstock. So now, what is this BitVMX that I've talked about? This is a project that is an open source project, a collaboration with several companies, including Roostock Lab and Fairgate Labs. And BitVMX is a secure, extensible, I would say soon to be open source, because we are going to do this very shortly, but it's not now. It's a framework for disputable computing on Bitcoin. And by disputable computing, I don't mean breaches. It can be anything. It can be channel factories. It can be payment channels with a new type of systems. I don't know, different, more private channels. I don't know, anything you want. And it can be like different L2 systems, right? So any contract you want to verify on Bitcoin, you can do it with this platform, which is agnostic to the use. So there is a history of different versions of this BitVM idea. So the BitVM, I would call it BitVM 0, or tap-leaf circuit, was what was presented by Robin in the foundational paper. And it's completely impractical, because you have to transform a program into a huge circuit, and that makes it very difficult to work with. But soon afterwards, Robin started working on BitVM 1, which is a CPU, which is much more practical because it allows you to write your programs, compile them, and run them on Bitcoin. But he abandoned this project. He thought that it was a better idea to create BitVM 2, which has some properties I'm going to talk more about later. And then 2 other projects came, Snarknado, BitSnark, and BitVMX, which is a project that Fairgate and Roostock Labs are collaborating with. And I'm going to explain a little bit about BitVMX and how it works. I'm going to dramatize it a little bit because I think it's the best way to understand it in just 2 slides. So normally in Bitcoin, there is a verification program, an input, also called the witness, and the verification program obviously can only accept or reject. Like it's a yes/no situation. And of course, the program is referenced in the output of transactions, and the script SIG, which represents the input, is in the transaction that consumes that output. And we have 2 parties, the prover, which is Patrick, and the verifier, which is Valerie, which she does nothing. She just observes that the script has been validated. In the BitVMX system, this is different. Instead of having one single transaction validate the program, we spread that into a direct acyclic graph of a covenant, actually, of Bitcoin transactions, right? So instead of having a verification program, we have a dispute resolution protocol. But all the rest almost stays the same. You have an input that is given in a Bitcoin transaction, it is signed, but now there is a role for Valerie, which is as a verifier to challenge if Patrick is trying to commit fraud. So this is the dramatization part. So actually, the protocol happens like this. Patrick says, OK, I'm going to withdraw my Bitcoin. This is the program input that makes the program accept. And then Valerie comes in, oh, no, you're a cheater. Let's resolve this dispute on chain. OK? And so Patrick says, OK, I'll build an execution trace containing state hashes of each step of execution and commit to it. Then we will bisect this trace until we find the disputed instructions. OK? So we have a huge amount of instructions in a trace. It can be billions of instructions. And then they both collaborate on-chain to find a single instruction that they know that the prior state is agreed and the state after it is in disagreement. So Valerie tells, tell me the state of steps X, Y, Z. And Patrick says, here are the signed mid-states on those states. So now Valerie has everything signed by Patrick and can go to the blockchain, go to a Bitcoin transaction and say, OK, please verify this single step of computation. So from a billion step, the blockchain only verifies 1 step. And this is where magic happens. Verifying a full payout of RISC-V would take like 50 gigabytes of data, of script. If we could compress this into a snark that verifies the same program, it would still take 2 gigabytes of script. But the maximum size of a tapped script is actually 400 kilobytes. Well, verifying a single instruction of a CPU can take a quarter of that 400 kilobytes. So that's how we do it. So BitVMX is CPU agnostic. Like you can code any kind of CPU you want. We have narrowed it and we have focused it in building a RISC-V 32-bit CPU. And why? RISC-V is open source. RISC-V is license-free. There is tool chains. You can write these programs in Rust, in C, in C++, whatever language you want, and then just compile it and verify it on Bitcoin. And the other important property is that we made it what we call dual input support. Like the prover and the verifier, both of them can provide input to the program. That's how we managed to put the interactivity part on the same program. Like the prover can put a snark or an input that says, OK, this is the best chain, in my view, and then the verifier can put an input herself and say, no, this is a snark that proves that there is a longer, a canonical best chain, which basically overrides your proof. And then one of them will lose this dispute. So I'm going to go a little bit faster. So we started with a very awful, inefficient protocol. We had 66 rounds. Like this dispute resolution protocol took more than 100 transactions, and it was kind of expensive. And we managed with different ideas to lower it and lower it, lower it. First, we took this approach of NR research, where instead of bisecting, we divide it into multiple intervals, and then one of the parties choose between these several intervals. It's a trade-off between space and rounds, but it's a perfectly good trade-off. And then we created a specific data structure for logarithmic connections of nodes in a DAG, something that a new data structure is something very rare. You don't get much chances of creating a new data structure. We did it. And then we created an optimization of this protocol, and we put this down to 6. Obviously, we need to code it. This is just in the paper, but we know we can do it. And in terms of cost, we also, with improvements, we think we can put down the cost from 600, that is yesterday's cost of the dispute, to only $65. Of course, we need some time to test this, but we think we can do it. So comparing some of these existing solutions, I'm not going to go in much detail in this, but there are 2 important points here. First, BitVM 2 is the only that has just 1 round. Basically, the prover says something, and then anyone can challenge in just 1 transaction. That is excellent. The problem with BitVM 2 is it's very, very expensive. Depending on the congestion of the network, it can cost between $10K to $200K to finish a single dispute. Where in BitVMX, the costs are between $380 and $10K. So the type of participants that can be staking in this system completely differs from BitVM 2 compared to BitVMX. So a little bit about, I have only 9 minutes, a little bit about the Union Bridge. This is very recent design. Like, we studied it in July in Roostock Labs, but I think we made incredible progress compared to other protocols. So we have a certain design goals. For instance, we wanted to have flexible management of security deposits and prices. And when you put the security deposits on Bitcoin, where all the other protocols do, it's terribly difficult to share the profits with a different formula. Like in Bitcoin, you have very limited ways of specifying that. So we decided to move everything related to management of security deposits to the Rootstock blockchain. And we wanted, obviously, to have cheap peg-ins, fast peg-ins, cheap peg-outs, fast peg-outs, and obviously the efficiency. It was key to have a capital efficiency of the security bonds. Why? Rootstock was created for financial inclusion, to let the unbanked, the people without, with capital controls, with a lot of problems with the hyperinflation, to be able to access Bitcoin and fiat currencies with collateral in Bitcoin, right? And we don't want to propose a new system that somehow restricts this. Like, let's only a few participants, big liquidity providers, be able to participate in the bridge. We wanted to keep the system for the people. So that's, for us, it's very important to have cheap peg-ins and cheap peg-outs. So the architecture, okay, so the only thing I'm going to mention here is that there is peg committees, and if all the peg committee agrees on a peg-out, the peg-out happens instantaneously. There is no dispute, there is no delay, and a peg-out can happen in only 10 minutes or 30 minutes, depending on the amount. All the problems happens, and all dispute happens if one member of the committee is unresponsive, it doesn't want to provide their own signature, and then the dispute protocol starts. So each member of the committee has a lot of responsibilities. Obviously, it's part of the committees. It has to be able to advance funds to the end user on dispute. So this is, I'm going to explain it later. It has to be able to create a snark proof of Rootstock withdrawal. And it is done by executing a light client in a ZK zero-knowledge VM. It has to monitor Bitcoin UTXO to be able to challenge the others. So many responsibilities. And maybe there lies some complexity of the protocol. The operator has to have his computer on at all times. So let me explain how it is the flow of a peg-out, because the peg-out is a key element of how it works. So first, the user commands the Rootstock bridge contract, which is a contract that already exists in Rootstock that manages the peg-ins and peg-outs, that he wants to peg out. He logs some Bitcoins, and then the bridge contract in step number 2 will request all the committee members to sign this request. Let's say one of them does not sign. Let's say one of them is unresponsive, non-collaborative, malicious, whatever. So what happens afterwards is, in step 4, is that the blockchain will pick one operator at random, and we'll tell this operator, hey, you have the responsibility to forward the funds to the end user, and then obtain proof and give this proof to the BitVMX protocol. And that's why in step 5, the operator will do. What happens next is that once the transaction is confirmed in Bitcoin, The operator takes this transaction, an SPV proof that it happened on Bitcoin, puts that on Rootstock. Rootstock has an SPV client. Rootstock is a hybrid federated peg. Everything that happens on Rootstock is already a validating bridge. What is not a validating bridge is what's happening in Bitcoin, but Rootstock already is running a light client of Bitcoin in consensus. So basically, this bridge contract can see this transaction and say, OK, it emits an event that says, OK, you are ready to collect the reimbursement. In step 7, the operator goes into the BitVMX protocol, does a kickoff transaction, and this kickoff transaction puts as an input the snark proof, OK? And then with this snark proof, everyone else is able to challenge. Let's say nobody challenged, then sometime later, he's reimbursed from the BitVMX protocol. So it's quite simple, right? So what about the efficiency of security bonds? This was one of the main problems we detected in the other idea. So what we did to be very efficient in the handling of security bonds is to packetize UTXOs. So instead of, as Rootstock is currently, that it has a big wallet with a lot of UTXOs of different values, and it has to choose, every time there's a payout, it has to choose which one to use, etc. We put all the UTXOs of the same value in what we call a packet, and then there is a following packet, and packets are set up in a sequence, and they are spent in first in, first out order, right? So there's a very specific order that's established how these UTXOs are spent. So in the right, we have the UTXOs that have already been spent. In the middle, the ones that have Bitcoins but have not been spent, the green ones. And on the right, we have slots that have been prepared. Like all the setup has already been made, and they just need just one transaction to be filled with the funds, OK? Now, what we can do is we let the operators, the members of the committee, stake or put the security bonds on this smart contract, and that smart contract manages putting the security bonds. And how it will do it, it will put one security bond per packet. So a single security bond covers a packet of UTXOs, and that's the key difference. In all the other protocols, a single security bond covers a single peg-in, because that security bond is on Bitcoin, right? So by moving the security bond to Rootstock, we can put a single security bond for a whole packet. Not only that, if I'm a user and I only have, let's say, 0.001 Bitcoin, I still want to participate, I can put my collateral in a stream that only has UTXOs for 0.01 Bitcoin. So I can be chosen to advance up to 0.01 Bitcoin, not more. But if I have 1 Bitcoin, I can register in a stream of 1 Bitcoin, so I'm able to forward 1 Bitcoin. So everyone can participate. So how do we solve the problem if we put all the UTXOs in the same packet to minimize the security bonds? How do we solve the problem that, if one starts a dispute, he can start all the disputes together at the same time? Or if one party is penalized because he misbehaved, how do we prevent this party from still participating in all the following disputes of the same packet? So this is a block diagram of how this DAG of Bitcoin transaction is created. And we have essentially 3 blocks. The dispute kickoff is the block where when the kickoff transaction happens with the input. And we have this enablement and penalization block that has one UTXO that is called the enabler for each operator and for each peg-in. So every time you want to do a kickoff, you have to burn one UTXO from a table of UTXO that are prepared for you. And so you burn this UTXO, and then you are able, because the kickoff transaction is burning that UTXO. So you have an enabler as an operator, and another UTXO you have to consume to enable as a watchtower. So what happens if you, in the pairwise dispute channel, is the part of the protocol where the dispute happen. If I lose a dispute, either because of timeout or I just submit something that is incorrect or whatever, then this goes back to the enablement and penalization block, because some transactions are enabled if I lose my dispute. And it will cancel all my UTXOs, all my enablers. So there is an incentive for all the rest of participants to prevent me from participating in any other of these pegging opportunities. And there is still one more mechanism that if a single operator opens 2 disputes at the same time, there is a mechanism, there is a single transaction that can cancel both disputes. So no operator is ever able to open 2 disputes at the same time. And that's how we managed to have very small, very low security deposits. OK, so I don't have much time. I'm just going to skim about the different properties compared with the POPEG, which is the current system, the Linux 24 breach, which was the paper that was published recently by Linus, which is another breach system. And so, first of all, the highest decentralization, I think, is on Linux 44 paper, because it's just one round. It allows anyone to challenge, although it's very, very expensive to challenge. It can cost like 20K grants, but it's a bit more decentralized. But we can handle minimum peggings of $200 because the cost of dispute is so low. While in the other protocols, for instance, in Linux 24, you would need at least, because of the dispute can be very, very high, you would need at least 100K. OK? And we can support any kind of integrity proof, computation integrity, Stark, SNARK, or Nova, or whatever, where the other systems are tied to a specific SNARK, because they are not general purpose, they are specific. And also, of course, because we have this dual input capability and none of the other protocol has, we can support full interactivity, proof, counterproof, etc. Of course, we have the lowest cost, and because we spread the security bond over multiple inputs, we have this. I mean, if you compare the amount of collateral you need for a certain scenario I created here, it would be like, you would need like 100% collateral for the Linux 24 breach, while we will take only 1% collateral. We have a roadmap in these 2 projects that are related, but not the BitVMX project, which is general purpose, and we are going to implement these optimizations I talked to you about, and make this open source, and make this well documented for anyone to participate. And then there's the Union Breach, which is a project that Rootstock Labs is pursuing. Well, we still have like 1 year until mainnet, because we take very carefully the security side, and there's a lot of funds at stake on Rootstock right now, so we need to be very careful on how we migrate from one system to the other. And of course, we need the community approval. This is not something that the community needs time to discuss this. So yeah, as a summary, I presented, sorry for the delay, the Union Breach, which is the first, I would say, permissionless and capital-efficient breach based on BitVMX. Rootstock Lab continues to develop this breach, and I invite you all to join our forces with the BitVMX framework, or later with the Union Breach to make Rootstock better. Okay, thank you very much.
You mentioned the beer event.
Oh.
Yeah, you should.
Thank you, Brad.
Sergio is such a nerd that he forgot that his company is sponsoring drinks tonight.
Yeah, 6:30, there is a meetup, Rootstock meetup. You are all invited. There will be drinks. Vlad will be there talking about all these podcasts he does. Yeah? OK, and I'll probably be there too. See you later. Bye.